Howdy, I'm Thomas Barth.
Howdy, I'm Matt Johnson.
Howdy, my name is Eric Noonan.
We worked with Dr. Gregory Huff on our senior design project for this school year. Our project is entitled Phase-Based RF Directional Tracking System. The goal of our project was to design a system that uses the phase difference between the signals received from a single transmitter by two closely spaced antennas to track the transmitter's angular location. The phase difference between two signals quantifies their temporal misalignment, or in other words, a phase difference represents a shift between two signals along the time or horizontal axis. A phase difference between two signals operating at the same frequency and in the same medium directly correlates to a difference in distances traveled. As demonstrated by this diagram, two closely spaced antennas will receive signals from a single transmitter with a phase difference represented by the symbols delta phi. The transmitter's angular location, represented by the symbol theta, can then be calculated from this phase difference using the formula shown here. The AD8302 chip measures the phase difference between two input signals by outputting a corresponding voltage as illustrated in this graph. The graph shows the chip's output voltage as a function of phase difference and the measurement error as a function of phase difference. It is important to note that the output voltage is at a maximum when the phase difference equals 0. Multipath effects refer to the fact that a transmitted signal does not just travel along a line-of-sight path from the transmitter to the receiver. Instead, as illustrated here, the transmitter signal travels in countless directions, reflects off the surrounding environment, and reaches the receiver along a plethora of different paths. The effects of this multipath behavior reduce the reliability of a direct delta phi to theta measurement and conversion. The delta phi measurement is most accurate when delta phi equals 0 and theta equals 0, meaning that the receiver is facing the transmitter. As previously noted, this condition corresponds to a maximum AD8302 output. A receiver can therefore chase the delta phi equals 0, theta equals 0 point to track a transmitter.
The final system consists of a mobile transmitter, the object to be tracked, and a base receiving station, pictured here, which rotates to track the transmitter and outputs its angular location. This diagram illustrates our system's physical and electrical interconnections. The RF transmitter is located in or on the object to be tracked, in this case, a football. This generates the signal, which is collected by the two receiving antennas with a phase difference. Notice that a ground plane is used with the transmitter antenna to improve its performance. The two dipole receiving antennas are mounted on a ground plane on top of the receiving station. These antennas each receive the same transmitted signal, but with different phases. The previously mentioned AD8302 phase chip takes the output of the receiving antennas as its two input signals and then generates a voltage signal based on the relative phase difference. Two Arduinos are used in this system because the two primary programs run on highly asynchronous timelines. Arduino 1 controls the rotation of the motor and the receiver system based on the phase difference control signal generated by the phase chip. Arduino 2, on the other hand, computes the transmitter's angular location based on the known rotation of the receiver station. The control circuit consists of an H-bridge, which physically controls the motor's direction of rotation based on the Arduino 1 control outputs. The receiver station rests directly on the motor's shaft. This allows the motor to directly rotate the receiver station to follow and face the transmitter. Two photointerrupters are positioned beneath the receiver station platform to track its rotation. These devices function as optical encoders by generating a pulse whenever one of the sticks attached to the bottom of the receiver station platform passes through their terminals. Arduino 2 uses this information to calculate the transmitter location. The graphical user interface outputs the transmitter's angular location as determined by Arduino 2. The user interface consists of both a numeric angular position indicator and a time compressing graph of the transmitter's angular location over the previous 10 seconds.
This diagram details the control system logic used to steer the receiver system and track the transmitter. The logic simply checks to see if the phase difference is close to 0 degrees and whether it is increasing or decreasing. The result of this check is then used to steer or stop the motor and receiver station. This flowchart details the control system logic used to track the transmitter's angular location with respect to the receiving station. The logic combines knowledge of the motor's direction of rotation and information from the photointerrupters to track the transmitter's angular location by adding to or subtracting from the previous location. The goals of this project were achieved, and the final system tracks the angular location of an RF transmitter as specified in the objective statement. Future research should be performed to develop a system capable of overcoming deleterious multipath effects and directly converting a measured phase difference into a transmitter's angular location to achieve a purely electrical tracking system.
Thank you for watching our video. We hope you enjoyed it, and we appreciate everyone who helped us along the way.